Are we ready?
We'll start in just a moment. It's just almost time. So we've started recording the presentation and we'll get going underway in a minute or so for those of you who are online. Okay, well, welcome everybody. Thank you for coming to our second Climate Science Informal Seminar Series. My name is Peter Jackson. I'm a professor here at UNBC, but also chair of the CMOS BC Interior and Yukon Center. So CMOS stands for the Canadian Meteorological Oceanographic Society. And so this seminar series we've had a number of years, not recently, but we're restarting it this year, is kind of co-sponsored by UNBC and by CMOS Local Center, as well as the Pacific Institute for Climate Solutions is also sponsoring this seminar series. I'd like to acknowledge that we are on the traditional territory of the Dene at the Cal First Nations. And since some of us are connecting virtually, let us also acknowledge the Indigenous peoples of all the lands that we're on today. We are using the Zoom webinar format for those of you who are online, which restricts your ability to interact, but there is the Q&A that you can submit your questions to later on, and I will read them out and ask them as we go along at the end of the presentation. And so at this point, I'd like to introduce Chibuike Onwukwe, who is a postdoctoral fellow here at UNBC. Prior to that, Chibuike was a PhD student, and he did his thesis looking at air quality in the Terrace Kitimat Valley, where he modeled the air quality in that valley and resulted in a number of publications. Since that time, he's been working on the project he's going to present today, and also on a new project, which he started recently on a heat dome event that occurred in June of 2021. Chibuike's presentation today is modeling the climatic impact of the Williston Reservoir on the Tsay Dene First Nation territory of northern BC. So Chibuike, I will turn it over to you, and I'll stop my video here.
Thank you so much, Peter. I'm very grateful to be here among this session and in your presence. And I'd like to thank you all for the good work you're doing at CSIS to bring this series, get it going. I'll be talking about the modeling of the climatic impact of the Williston Reservoir on the Tsay Dene Nation territory of northern British Columbia. I kind of started this project sometime last year, and it was due to concerns, about the local concerns in the community that the Williston Reservoir is impacting on livelihoods, is impacting on the human comfort, is impacting on the way of life. But there are so many social issues concerning this reservoir, but I just concentrate on the impact that this reservoir is having on climate. Before I proceed, just to kind of give you people a kind of heads up about, when we say climate change, especially when we don't have a way of recording or making observations, most times we mix up the notion of climate and that of weather. So, for instance, when I say from lived memory, the weather is changing, you are kind of considering just the short term, okay? But when you say climate, it's something that is more of a longer duration in time. So, for instance, if we say that climate change has occurred, you have to, be sure that you have collected data for a very long period of time. And this is what we, mean. For instance, you kind of take a monthly means of, say, for instance, temperature. Then over time, you compare it between another period in time in past, and then you can ascertain whether there's actual change in climate or not. And when you talk about climate, it's not just one variable. Like here, I just presented the analogy of a temperature or time series. You can also talk about wind speed. You can also talk about precipitation. And you can also talk about sunshine, that's insolation. But the fact remains that for you to analyze climate change, you have to first of all collect data on weather and keep it for a very long period of time. So there's this notion that weather is what you get, but climate is what you expect. So if you are going to a very, a new city, you have to take into consideration the climate. Now, over time, we've had this concept that the global climate has changed, right? So we now talk about global warming. Global warming is just just an instance of climate change. Global warming is not everything about climate, it's just an instance. But that has been the main indicator to tell that, the world climate has changed. So if you look here, you could see that between the past 200 years or so, scientists have discovered that actually the global temperature has increased by approximately 1.1 degrees centigrade. And now this increase is mainly driven by human and also natural drivers. When you say human, like we often think about the carbon emissions, the methane emissions, which are greenhouse gases. So they're kind of the contributions from human sources. Now these greenhouse gases warm the earth and kind of drive the increase in temperature. But if you are looking at it, actually, you'll see that this increase has just occurred over the past, say, 75 years or thereabouts, because it's starting from around 1950, right? So that's just, you have this steep rise. So if you look here, you find that natural drivers, if you are just, when you say natural drivers are like volcanic eruptions, right? So these are, global climate has a way of recalibrating itself, even if there's a perturbation or kind of a forcing effect, it has a way of going back to normalcy. But because of human impact, because of human activity, we have this spike. But this is just a kind of a microcosm of climate change. Now, what are these impacts of climate change? The impacts, as you know, we have this melting of snow, increased melting. They have droughts in some parts of the world, especially where you have people rely much on water resources. Okay, so sometimes you have also countries that are in conflict because of maybe damming, or maybe trying to make use of hoard more water so as to use it to themselves. So these are kind of challenges that have come from having this problem we are facing with warmer climate or general climate change. We also have the impacts caused by rising sea level, okay? Because when these waters melt from glaciers and all that, they kind of make the water level to rise and flood many areas. Last year, I think we had this, the extreme heat temperature. So these are kind of, these are signals. Okay, these are signals that our climate is changing. Now, when we talk about climate change, like I said, there are different drivers. Okay, people tend to focus on emissions, carbon emissions, and profile solutions to that, maybe through tree planting, through having more forests and all that, and also through city management, vehicular management, trying to curb fuel burning of fossil fuels and all that. But there are also, even without having emissions, by the mere fact that because these emissions exert the influence through changing the atmospheric radiative fluxes. So by just changing the surface, you can also have a change in climate. For instance, let's say for urban areas, when you talk about the urban climate, you find that when you have more buildings, you have walls that retain heat. So you have these urban heat islands, coming, playing their role. So you don't need to actually emit to have climate change. You can also, just by changing the land surface, you can have an effect, and that's part of the human effect on climate. Now, this has become, the modification of landscape has become quite an interesting topic. Some people have looked at the modification to get, to have more irrigated croplands, okay? So maybe due to the, pressure to grow more food crops. So we have people, governments, having irrigation systems. So these different studies have been conducted, especially in the western part of the United States, about the effect of having modifying the land use into irrigated croplands, and the impact on regional and local climates. But these are kind of more like smaller scale studies. But there's a recent study that just came out examining the impact of water reservoir expansion globally. Okay, and if you look here, this, the authors, Van Decken and co-authors, they kind of looked at, they use a model, a climate model, to simulate the impact of having more reservoirs across different countries around the globe. And you see that they are actually isolated that most of the impacts that come from reservoirs are in those areas that rely on water resources that already have created dams and hydroelectric power. So, and if you look at this scale here, because it's like, if there's an increase, then you have this positive signal, which are colored here. You find that parts of the northwest of North America has, has high impact. Also, looking at that of Russia, because they have a lot of hydropower projects. So these impacts are kind of correlated with where you have more use of water resources as hydroelectric power projects. But outside these regions, that's the, kind of outside the North America and Russia, so most of these places don't have much of these impacts because of maybe their lower scale, or maybe the climate is not so sensitive to this kind of projects. But the main thing is that the forcing from reservoirs can have quite an impact on the global estimates of the change, from human activity. Like when we said that there's a projection that the global climate will change by at least by 2 degrees centigrade by the end of in the next 100 years. So you have to factor this kind of activity into this sort of projection, because if you don't do that, then maybe your resiliency programs or your the mitigation programs that are being planned might not really be very effective. So this has spurred part of this kind of concerns has spurred me to, especially when you look into the situation that is taking place with the Williston Reservoir. It's spurred me to kind of look into this sort of impacts at a regional and also at a local scale. So in this instance, we look into the impact of the Williston Reservoir climate of the Senekene First Nations territory. Now, this area is kind of a bit remote. In fact, it's remote because it's just tucked into the Rocky Mountain ranges, right? So you have these high ridges flanking this reservoir, because this reservoir is quite a massive project. It was created in 1960 from the damming of the Peace River and Finley River that joins this Peace River, because there's previously there are just rivers, but from the damming further downstream here, you had this massive reservoir, which you now call, it's kind of artificial lake, right? So the lengthwise, because if you look here, it's not so straight. So north-south is about 255 kilometers. West-east is about 155 kilometers. The surface area of this reservoir is 1,761 kilometers square, and the average depth is 42 meters. So making it the largest artificial lake in BC and the second largest by volume in the whole world. So you kind of can start thinking about because this size is even the size of some states, like some countries. So if you can imagine that this is a very large modification of the landscape. Now, because the area doesn't have much observational data, because in order to kind of tease out the if impact this reservoir might have on the area, we are supposed to have maybe used past observational data, right? And then that's before the creation of the lake. And then after the creation of the lake, you now compare the data with the both sets of data, and then find what impact the reservoir might have on the area. But because we don't have, there was not much monitoring, as at that time, 1968, there was even up to now, there's not much, long-term data. So we had to use a modeling approach, using a numerical model, that describes the atmospheric system in a way that is quite representative to this area. So the name of this model we use is called the Weather Research and Forecasting Model, which is abbreviated as WRF. Now, WRF is a sophisticated model. It is used for numerical weather prediction, but it's also used for climate. You can use it as a climate model when you use it to kind of pull some climate data into a region of focus. So this is what I used. But the main addition to this effort is the use of a lake model. And now, because this, when I say lake model, I'm just describing the Williston Reservoir as an artificial lake, because it's not a natural lake. So, when you use lake model, when I say lake model, yes, it's a reservoir, but here I'm just picking it as a lake, which is sort of maybe a shortcoming, sort of. But that's not to kind of say that the approach I'm using is not reliable, because you have to input so much data. Even if you don't have real-time data, you can use data generated from other context models to input into this model and run it, and it will give you several variables which you can use to characterize or quantify the effect of the modified landscape on climate. Now, this is what I kind of did, because the area is quite small related to the available large scale data we have. So first of all, you have to kind of regrid the large scale data into the small scale area, which I kind of this is what we call downscaling. So we have to run the model like 3 times just to kind of reduce the spatial scale of our focus up till this area where we are interested in. Now, these are the sizes of the grids are used, but what we are kind of concerned is about the smallest domain size, which is the Dene Nation Territory area. And so this area I show here is gridded into 121 by 106 grid cells, each of them measures 1.6 kilometers. And now recall that this using this computer model is kind of quite expensive in terms of computation because of the fact that we are running this for each hour. I'll come to that. For each hour and for each cell. And I use the terrain resolution of 30 seconds, which is like approximately 1 kilo. So the terrain resolution is matching with about the size of the grid resolution I'm using. Now, in order to kind of do this modeling appropriately, because one of the problems was how to generate the past terrain of the area. That's what was the land cover of this area before the creation of the dam, of the reservoir. And so we have to kind of go back in time, pull out data, kind of use the topographic data, change it to the grid cells of the of that neighbors to the that's neighboring to this water surface, so that you have 2 sets of scenarios. The one that depicts the presence of the reservoir, which we call the wheat rest, and the one that doesn't have the reservoir at all, which is the no rest. Okay, and with these 2 sets, I plug it back into this domain, this small area, and they run the model for 10 years. Because I just wanted to capture the kind of variability that might occur in the atmosphere over this period. Because if you use like 1 year data, it might be kind of biased in a way. Because, for instance, last year alone was a kind of have very high temperatures. So you just need to mix up the atmospheric system just to capture the kind of the whole range of conditions that the area might be exposed to. But this is what it looks like with the approach I'm using. So I did this simulation trial for a long time and got hourly output. Because it's hourly output, so it takes a lot of resources, it takes a lot of space, it takes a lot of time. It also takes a lot of computing. But at the end, I got the output. Okay. So one of the things to watch out for when you are using this sort of approach is to examine if what you are getting is reasonable, because it's like a model. It's reliable. The model is reliable, but it has to also check, because when there's so many input that goes to it, you have to put in the meteorological data, you have to put in the terrain data, you have to put in some, if you are nudging the system, like if you are kind of using some observations, you also want to see if they are being caught. Also for the lake model, you want to make sure that there is a sort of, the model is recognizing your input, sort of. So in this case, we kind of focus on the key variables, that can use to describe, a climate of a place or a region. Now, if you look here, you see that I kind of split this data into different seasons. And one is the summer. Summer, if I say summer, is June, July, August. Fall is September, October, November. Winter is December, January, February, and spring is March, April, May. And then you have the annual mean. So if you look here, I mean, I don't know if the audience is kind of catching this scale here, because it's kind of blocked a bit. But if you look, you find that there's sort of consistency, because this, I think, reaches up to 16 degrees in summer. And looking at the TD, which is the dew point, okay, dew point is the temperature at which the air is saturated. So it falls less than the air temperature, because if it is same, because dew point cannot be higher than the ambient air temperature. But if it's less, like this color is, this color is less than what is color. So it seems that the kind of consistent. And looking at the wind direction, because in summer, because generally for the area, you have this system that blows from the west towards the east. So it's kind of representative, except for maybe in the winter, because you have the winter storms, and the circulation is a big drag in winter. So because you have outflow winds, kind of different directions, but it's also representative, because the general pattern of west to east flow is represented. Then you have the precipitation. I'll come to this later on, but you find that in terms of model consistency, you find that the higher elevation areas have more precision, because this area relies more on the orographic precision. And even if you look at the pattern, you find that the summer, because summer is when the area generally gets its highest precision. So you find that the shade here is darker than other seasons, because the other seasons don't have as much precision as in summer. Now, do they actually match with what other data that exists? So this is where we have the evaluation. Now, what I compare my outputs, I compare with a data they call Dene. Dene is a 1 kilometer grid data, but it's kind of the statistical computations to retrieve, kind of estimate this variable. So it's not actual observation, but it's close to observation. So, but you have biases, right? This was when you subtract, I subtracted my output from Dene and getting these differences. So, for instance, in most of the range is between 2 and 3 degrees, but not more than 2 and 3 degrees for across the seasons. In fact, most of it was like within 1 degree difference, across seasons for air temperature. Therefore, dew point, which is a measure of humidity, because dew point is like it tells about how close the air is to saturation. So the dew point is not it has a higher bias, because there are some other variables are linked to dew point because of the water vapor, because it's kind of a real measure of humidity. But much of the bias I had was, because the wind speed was kind of quite bad, especially in winter. We have, I think there's so much forcing of the synoptic flow on the model during winter. So, and this is a complex, and in fact, it's actually this kind of biases are recognized over very raw topography. So it's not something unusual. Then, one other key thing to look out for is the ice in the phenology, because this we are dealing with a reservoir. So what you see here is like the evolution along the center line. Like I took a transect along from the north towards the south of the reservoir, and kind of plotted the temperature profile. Okay. So what you see here is the modeled temperature. So yeah, I mean, this is consistent with what you may kind of because this is the scale here, right? So, but this other scale is for the ice fraction. So the ice fraction, I have data for it. Like I got a kind of data from a Canada Ice Service, but it's kind of it's only one measurement in every 2 weeks. So it's kind of averaged, for these 10 years. So it's like, that is not, the data is not complete, but from what we have, except for maybe the timing, but the shape, it's just the timing. So if, for instance, for the freeze over period of the ice, so you are kind of having a kind of a difference of 2-3 weeks, but for the melt period, so you have like 1 month difference. But generally, if we had observational data for the temperature, lake water temperature, that would have been better to compare to. But overall, when we look at, when we kind of compare other studies, like these are studies that have also used model to assess the climatic effects of lakes. So we find that while our work is maybe comparable or even slightly better than some of these efforts too. So overall, we just, the air temperature on annual scale the bias is 0.1 degrees. The wind speed is 1 meter per second difference because we predicted higher wind speeds. And then the precipitation is still within a factor of 2 when you're talking about the percentage. So, but most of the biases are more like during winter, where you have this strong forcing of synoptic data. Now, to kind of start isolating the impacts, okay, I kind of subtracted the no rest from with rest and then found these differences. Now, the key points are, first of all, for temperature, you find that the temperature is this reservoir has a warming effect in fall. That's between the period between September, October, November.
Chibuike, you can hit the X on that little black thing to get rid of that.
Okay, so yeah, so you have sorry if you didn't get it. So these the air temperature is at maximum air temperature, this minimum, these are dew points, right? So you find that the greatest, have a kind of warming effect in fall for the air temperature, and which is like up to 1.2 degrees centigrade change, okay, for about 2 to 5 kilometers of the surrounding area. Now, what you see here, the gray marks here is where these differences are significant, where these changes are significant. So it doesn't matter whether whatever value it is, but wherever I see this ash dots, it means that these points are the places that the differences are significant between having reservoir and not having reservoir. Now for the Tmax, the general effect is that of reducing the maximum temperature. So instead of having, a higher, it just reduces the maximum temperature. Whereas for the minimum, it just increases to an extent, except in winter where you have, there's almost no, just kind of quite different from the others. But the most important thing here is that fall seems to be like the period when we have a kind of observable notice on the effect of the reservoir on the surrounding climate. Now, why is this so? Why is the fall season or warm season kind of important in this for temperature? Recall that, like I said before, the part of the influence or that could have on climate is just by changing the surface radiation property. So here we have different seasons, but it's only winter that you have an increase. Now, Abedi is like the the amount, the fraction of incoming radiation that is solar radiation or sunray radiation that is reflected from the surface that doesn't get into the ground. So just once it touches, it bounces off from the surface. So here you see that the winter season has, by replacing the original terrain with reservoir, you have a higher albedo, right? So because of the fact that the winter season have icing, because once the formation that's, now you have the reservoir, is able to form ice over here. So if the incoming radiation bounces off, right? But this was, you have the water, so which can absorb more incoming radiation. Okay, so what you are just looking at here is different components of this the net radiation. I've just listed them here, but the more important is that if you look here, right, we are looking at this sign, this line here is the ground heat flux, because the ground heat flux with the reservoir it has a high heat capacity, so making it to absorb more of the incoming radiation. So if you look here, much of it is negative because it's kind of a very massive body that can absorb heat. And then if you look at the differential, you find that for the latent heat, because the latent heat is the heat that is available to evaporate water. So the latent heat is only much more positive. That's capable of evaporation only around the fall season, even for the sensible heat, because in here is able to capture a lot of energy and then release it slowly, because in summer you have that this the solar radiation, which is K star, absorbs energy, then keeps it and then releases it in fall. So that's why here when I showed the previous slide, we had more impact on temperature in fall season. And for that reason, when you look at the whole kind of effect, you find that generally there is the kind of increase the frequency of warmer days. For instance, what number of days exceed the median of the no rest value? You find that it's up to like 5 days that exceeds the median of the no rest. So, but these are not, because this is a temperature, so it's not as if there's the increase in temperature is so discomforting. Because if you look here, what they call the cooling degree days. The cooling degree days is how the number of the hours that exceed the 18-degree mark. So if you have an increase in cooling degree days, then it means that you need more air conditioning. But here it doesn't seem that there's a need for air conditioning. There's increase, but it's not like discomforting, right? On the contrary, you have that there's a kind of a decrease in the heating degree days. The heating degree days are days that when the temperature falls below 18 degrees, so you will need more like heat, kind of to keep warm. So in that case, it reduces it. The warming kind of makes the cold bearable, sort of, And also in the terms of diurnal range, there's a decrease in the diurnal range, like by up to like range of 2-3 degrees, for over the reservoir, but over the surrounding, like 5 to 10 kilometers around it, it's just like 5 degrees change. Now, wind is also a kind of parameter we'd like to look at just quickly, because this has been an issue. Just while I was in there, I kind of got feedback that there's a lot of kind of particulate matter pollution due to strong winds, and this is what the what that also kind of suggests, there's an increase in wind speed because this reservoir provides a smoother surface. Okay, because without the water, the air wind blows across, but with the reservoir, there's less friction surface, so there's a increased wind speed, and due to the fact that in reality that this reservoir kind of the water level goes fluctuates, so sometimes the wind kind of that comes kind of blows this particular the sediments within it spread it across. But what is more important here is also the significance. Like you also see the fall season having a larger amount of kind of greater significance compared to other seasons, right? So in fall we have that most are up to like 25 kilometers, okay, from the edge of the reservoir is have this show that there's the stronger winds. Then in terms of the direction, you can find that this because one see as kind of positive and negative directions, and the spin, like there's a kind of because if you have a positive direction change here, it means that the wind is kind of deflected a bit clockwise, but the area of this spin is kind of matching with the same area of this annual wind speed signal. Sorry, so that's kind of quite interesting because I didn't expect to have this kind of coincidence. So what you see here is the annual wind direction change, for wind. Now, again, just comparing the different percentiles, like, the daily wind speed, how was the incidence? So I find that up to like 60 to 90 days, exceed the previous value for areas just close to this reservoir, like within the nearest 5 kilometers. You have the, more frequent, that's more frequent periods of stronger winds. Then on temperature precision, we have this information that there's kind of a decrease in the summer precipitation, general decrease. And like I said before, the summer season is the main season that for precipitation in the area. And you find that, so because of this decrease, it also trickles down to the annual average. So you have here, there's a slight increase in during fall, but because fall cancels out much of the, this spring, cancels out much of the, fall. So you have this kind of reflected in the annual total. For the water equivalent of snowfall, you find that there's also a decrease in the amount of snow, especially in spring. We have this very strong signal for decrease in snowfall. And also for the fact that the area is now overlain by water surface, so we don't have kind of snow accruing over the previous area. So maybe this is a model representation, but it kind of looks realistic. Now, what's the reason for this? And when I checked, I found that because this area, because much of the precipitation comes in summer, and it's more like convective precipitation. So we have that, there's not enough lift, to take the water vapor towards the mountains to cause a precipitation, because of the, this surface now provides a kind of, it stabilizes the atmosphere. So there's not, the cloud, the convective clouds doesn't rise as much as to cause precipitation as before. And which is also reflected in the maximum convective available potential energy. That's the energy that is supposed to push vapor towards the mountains. And when I also looked at some of these some other variables, like this is along the transect along the lake, you find that even though the lake provides enough vapor, moisture, but it needs to be pushed. It needs some kind of an ascent to get towards the top of the mountain so that to condense and form. So if you are looking at here, you see that that kind of signal that shows that the vertical force that is needed to carry the vapor is not there in summer, but it comes up in fall when we now also notice that there's a slight increase in precipitation. So overall, we find that when you kind of quantify the effect, we are looking at around approximately 15% decrease and about 180 meter, in terms of quantity or in precipitation. Also a decrease in snow or water equivalent of snowfall. Now, I just kind of just to give a bit of context, because this we're seeing this all because these are kind of general area, but what of the particular community, like if you look very closely, if you notice in the first few maps I showed, you find that the community is just at the tip of the lake area. So what is the experience? So I just kind of pulled out data for that location, and it also shows that there's a kind of decrease in the diurnal range. So it doesn't get as cold as it used to be, okay? And looking at the monthly profiles, you find that okay, that these are also the things one might kind of get to experience. For instance, for temperature, like I've said, the temperature, that's kind of a warming, which is also reflected here, like this is the actual, with rest. Then these are the residuals. That's with the with rest minus no rest. So you kind of look at the profiles for different modes. So you have to find out the general pattern is that of an increase in temperature. Then there's not much increase in relative humidity, because I didn't talk much about that, but if we kind of recall, I kind of spotted differences and slight increase in the dew point temperature, especially when on warm days. Then we'll also talk about the wind speed increase, which is for every month, you find that there's an increase in wind speed. The diurnal range is reduced for the most part. Then the precipitation, there's a decrease over summer, and also for water equivalent of snowfall, there's a decrease. Mostly for the fall and also summer. That's especially if we are considering the effect of the topographic accent that no longer happens. So in conclusion, I detected a greater decrease in precipitation at high elevation, that's east of the reservoir, than at low elevation, up to 180 meter reduction in total precipitation of 15% decrease occurred over high elevation areas. There also increased in annual mean temperature by 0.2 to 0.5 degrees. So due principally to warming in the fall, because the warming season, the fall has up to 1.2 degrees change. That's increase in temperature. Increase in dew point by about 1 degree minimum on days when the air temperature is greater than 18 degrees centigrade. Increase in annual mean wind speed by up to 0.5 meter per second for 5 to 13 kilometers from the reservoir shoreline. And because of this, because some, this also have the ecological implication, like if we have the, increasing dew points, so because some plants, they just may survive only on dew, right? So that kind of, because of the requirement to have more condensation at a higher temperature, then that might also be a problem for some of these plants that just need the moist, just moist air. So my thanks to UNBC professors Peter Jackson and Stefan, he just left now, and Siraj and Brian. They've given me a lot of support for this project. I thank you all. And also to Chibuike Environmental, which are partners in the Tsay Dene area, Christine Marini and Mike Tyson. I thank you for your attention.
Thanks, Chibuike. So we do have some time for questions now. We've got about 10 minutes left. For those of you who are online, please submit your questions if you have any in the Q&A box, and I will read them out to Chibuike to answer. And those in the room are welcome to ask your questions verbally, of course. Go ahead.
Do you think that logging that's taken place around the shorelines and on the hillsides has had any impact on, both temperature and precipitation?
You mean logging? It's hard to say because the model it's not like an ecological system model. Like it just takes input as meteorological factors, like but it's something that is extensible. Like if I have
I've been on Williston Lake since the early 70s.
Yeah.
And at that time, they're just starting to log around, clear cut logging.
Yeah.
And, I see it now. I mean, there's tremendous areas that have lost its forest, the original forest. And I mean, the second growth coming up, but it's a very different type of forest that's around the lake to what it was at the time the reservoir was built, and for a few years afterwards.
Yeah. Much of the problem from the maybe you mean regrowth of the the plants there could be that maybe they might solve the problem of the air quality problems that are over having there, but aside that, I don't really know much about if that will kind of contribute to the climatic issues.
I mean, it's something that could be done, right? Like we do know that a clear cut is a different microclimate from a forested area for sure. And so what you're talking about is converting the shoreline from a forested area to a clear cut.
That's right. A little impact on the changes in temperature that you're talking about here, changes in precipitation.
I'm not sure the model scale would, at 1 kilometer horizontal spatial resolution, would necessarily be able to detect that.
Yeah.
But it's an interesting question for sure.
Because it's happened all the way around the lake. I mean, all the way up. Everywhere.
It's made it possible to easily log the near shore areas of the reservoir. Yeah. Any other questions in the room here or online?
I have another question.
Okay.
Could you please that slide about the delta minimum temperature and maximum one? I just didn't understand something.
Okay.
A little bit. Yeah.
This one?
No.
Okay.
Yeah, this one. In the fall,
Yeah.
I see that. Why is that red? Because usually in fall it should be the minimum temperature in fall.
Yeah.
So would you please explain that? Why is that red? Because
You mean here, right? So
yeah, exactly.
here, I think because the minimum is the minimum temperature is a lower temperature, right? So and you already have that for the average temperature alone. The average temperature is just a kind of warming effect, right? So if it is lower, then you also, because the average temperature is higher than the minimum, and for the average temperature, you already have a warming effect. So, I mean, reasonably, or I mean, I've not thought about it, but since the average temperature is higher, then you will also have a warming effect on the minimum temperature.
So the heat's accumulated in the lake, in the reservoir all summer long. So
Yeah.
the lake is relatively warm compared to what the land would be if there were no lake, which is why it's positive.
Yeah.
Especially in the fall, because the accumulation
Yeah.
is maximal in the fall at the end of the warming season.
Maybe we could go back to like what I showed here. You see the late, because these are the sensible heat. So the sensible heat is positive over the fall. So, and already, because these are average values, these are not minimum values. So already it's causing an increase over the average values. So invariably it lead to a kind of increase over the minimum values too, because the minimum value is quite low than the average.
So that sensible heat represents the heat flux from the lake.
From the lake
to the air,
to the
which
air.
warms the air temperature up.
Yeah.
And it's maximized in the fall when
Yeah.
the lake.
It's kind
accumulated
of,
the most heat.
yeah.
So there is a question online from Brian Manunas. He comments, nice presentation, Chibuike. And he says, if you could do this study all over again, is there anything you would want to change in light of your results?
Well, let me think about, because I don't think I missed anything. Maybe it could be to more than a high resolution, like 1 kilometer.
A higher
A
resolution.
higher resolution, like 1 kilometer. But I mean, I'll kind of use the rotated grid system so I could, kind of buy more space. Like, if I use rotated grid, then the domain will be kind of, just encompass just the very narrow points here. That if I had rotated it, so I could have gained more space, to use at 1 kilometer resolution.
Right. So you
Okay.
could have higher resolution,
Yeah.
but perhaps not as many grid points.
Yeah, man, I get, yes, yeah. So that's what I mean. That's just increase the resolution by using a rotated grid, so that I could maybe get. But I mean, I don't know if that will improve the result or kind of show something new.
Mhm.
But I don't think it will show anything new.
So a lot of, I'll have a question for you. So a lot of your results are kind of what we thought we might see,
Yeah.
based on our understanding of the heat capacity of water and converting water to land, or land to water. What would you say is the most surprising result of what you found? Would it be the precipitation changes or something else? Like what surprised you the most about what we saw in the outcome of the result?
I would say it's about the precipitation in summer, because I was feeling that since we have, this is a moisture source, like the reservoir is a moisture source, so that will fuel more precipitation.
Might have thought it'd be more precipitation.
Yeah, more precipitation. Yeah, but I kind of also, when I kind of look, kind of try to wrap my head around it. First of all, is this just a pure a water surface? It's not as if it is used for irrigation. If it were used for irrigation, you have a soil, right, on that, so which could kind of fuel precipitation.
Yes.
But it's just kind of a mass of water, and which in this case kind of stabilizes the air.
Right.
Yeah, because there was a study by Long et al. He did something with some of the Bear Lake and Slab Lake further on, when he just kind of idealized. So he used, where he just used a kind of where only a standing water body, and if that water body is being used for irrigation, because if in that case, the lower boundary, you have a soil, you have land, which kind of have this, evapotranspiration and,
yes,
some other processes linked to it, which might generate, but in this case, there's just a pure water mass of water standing. And
So the cooling effect of the water in summer stabilized the atmosphere, resulting in a 15% decrease in annual precipitation, 180 millimeters, which is quite
Yes.
a lot.
yeah, and because
Higher
because I kind of was, even when I got the results, I was kind of marveled. But when I looked at some of the reports too from the natives, and they kind of think, anecdotally, they say, "Oh, rain has stopped. They are kind of getting drier," kind of sort of corroborating this sort of results I'm getting. So, yeah.
Well, thanks very much, Chibuike. I think we're just about out of time now anyway. So thanks very much for those who attended. So thanks very much, Chibuike. Very interesting. And I will stop the recording. So.